Welcome to this video. Today we are going to understand one of the most groundbreaking innovations in the field of AI, which is transformers. We'll explore how they came into existence, the problem they were designed to solve, and how they revolutionized natural language processing and other tasks in AI. We'll break down the architecture of transformers, explain how they work using examples and analogies, and walk you through why they outperform older models like RNNs and LSTMs. By the end of this video, you will have a clear understanding of the core concepts behind transformers and how they have reshaped modern AI. So let's get started on this fascinating journey into the world of transformers. We'll start by discussing why transformers matter. Transformers have become the foundation of modern AI, powering influential models like GPT, BERT, and T5. These models have had a tremendous impact on natural language processing tasks, revolutionizing how we handle language understanding and generation. What makes transformers stand out is their shift from the older sequential processing methods used by models like RNNs and LSTMs to a more efficient parallel processing approach. This change has dramatically increased their scalability and speed, allowing them to handle larger datasets and more complex tasks. The influence of transformers isn't just limited to text. They have expanded to other domains, including computer vision through vision transformers and even into audio processing. Their versatility allows them to be applied to various tasks such as language translation, summarization, text generation, and even image analysis, making them one of the most powerful tools in modern AI. Transformers have revolutionized AI not in just terms of performance but also in terms of their ability to handle a wider range of applications across multiple fields, making them indispensable in today's AI landscape. Now that we have covered why transformers are such a game changer, let's take a step back and understand what the landscape looked like before their arrival. Before the rise of transformers, models like recurrent neural networks or RNNs and their more advanced counterpart, long short-term memory networks or LSTMs, were the go-to methods for handling sequential data like text. Imagine trying to follow a conversation where you only remember the last sentence said. This is how RNNs process information, relying heavily on what just came before. While this method worked for shorter, simpler sequences, it faced significant challenges when dealing with more complex or lengthy data. Now, to make this even clearer, let's try to understand it with another example. Picture this. You are reading a book where understanding one page depends on reading the previous one. This is how RNNs and LSTMs function. They process information in a stepwise manner. Each word or data point is processed based on what came before. Just like how you can't skip to the end of a book and expect to understand the whole story without reading the previous chapters, the sequential nature of these models meant that every step was dependent on the one before, making it challenging for them to keep track of longer texts or more complex sequences. While this page-by-page processing works for short sequences, RNNs and LSTMs struggle with something called long-range dependencies. To give you an example of this issue, let's say a model is analyzing a long document. Something crucial to understand the ending of the document might have been mentioned early on, but by the time model reaches the end, it has forgotten the earlier details. This inability to capture and retain information over long sequences severely hampers the effectiveness of RNNs, especially in tasks like language translation or understanding long text. Another major issue with RNNs is that they face a fundamental challenge during training. In deep neural networks like RNNs, when training over long sequences, the gradients, basically the values used to update the model, can either shrink to near zero or explode to extremely large values. If they shrink too much, the model can't learn from earlier parts of the sequence, which is known as the vanishing gradient problem. If they grow uncontrollably, you get the exploding gradient issue, which destabilizes the learning process. Either way, it makes it difficult for RNNs to effectively learn over long sequences, resulting in poor performance on complex tasks. And lastly, the issue with RNNs and LSTMs is that they process data sequentially. Each data point or word is handled one after another. While this seems intuitive for processing language, it introduces a big problem, which is speed. RNNs cannot process words in parallel, which makes them incredibly slow, especially when dealing with large data sets. This lack of parallelism makes scaling these models difficult, which is crucial when handling tasks with massive amounts of data, such as translating entire books or processing millions of emails. Now, we have seen how earlier models struggled with issues like long-range dependencies and insufficient sequential processing. Next, we'll explore how transformers were born and the key innovation that changed everything, the attention mechanism. So let's look at how this development paved the way for modern AI advancements. Introduced in 2017, transformers brought a significant shift in how we handle sequential data, especially in natural language processing. They broke free from the limitations of sequential models and introduced a whole new approach to understanding the context in data. At the heart of this breakthrough was the attention mechanism, which transformed the way models could focus on different parts of the input data. In deep learning, one of the key breakthroughs that changed everything was the invention of the attention mechanism. Think of it like reading a book. Instead of going through the pages one by one, imagine having a highlighter that can jump to the most important parts of the book, no matter where they are. This is essentially what the attention mechanism does. It allows the model to focus on the most relevant information, even if it's far apart in a sequence. This concept was revolutionary because up until then, traditional models like RNNs and LSTMs could only process sequences step by step. In 2017, the paper Attention is All You Need introduced the transformer architecture, which took this idea of attention and completely replaced the need for sequential processing. Before this, models like RNNs had to process data in order, which made them slow and prone to losing important information. But transformers changed that by allowing the model to look at different parts of a sequence simultaneously. This breakthrough paved the way for models like GPT and BERT, which have transformed fields like language understanding and generation.